We will generalize now the idea of linear transformations for any vector spaces. So we are going to say that a map from V to W, where V and W are vector spaces, is a linear transformation if, when we do the transform of an addition, it's the same thing that doing the transform of one, the other, and then add them with the addition in the second vector space. And when we multiply a vector in V by a scalar, it's the same thing that transform the vector and then do the scalar multiplication in W. In other words, a linear transformation separate additions and take the scalars out. For example, let's consider this map. Let's see if this map is a linear transformation. This is a map that goes from the vector space of the polynomials of degree less or equal than 1 to the vector space of the polynomials of degree less or equal than 2. And the transformation is this one. It takes a polynomial, generic like this, a polynomial of degree 1, and transform it in one of degree 2 in this way. What it's doing is multiplying the whole polynomial by x, right? A plus bx gets transformed in ax plus bx squared. So let's see if this transformation is really a linear transformation. So we need to prove the two properties. So for the property 1, we will do the transformation of an addition of two vectors. Let's take this vector, a plus bx, and add to another vector, a prime plus b prime x. So this we will need to check. We don't know if this will be equal to the transform of the first vector plus the transform of the second vector. And so we do these two operations in both sides, left and right, and check if they are equal or not. So for the left part, we need to do first the operation between parentheses, that is an addition of polynomials. This is a plus a prime plus b prime x. And now, still in the left part, we actually do the transformation. We apply the transformation t to this polynomial. Let's see what this transformation is doing. It's taking a polynomial that has a component plus another component x. What it does? The first component x. So in this case will be a plus a prime x. What else? Plus the second component b, that in this case is b plus b prime x squared. So this is what this transformation does. We did calculate the left part of the expression. Now let's calculate the right part. Let's transform the first polynomial. According with this transformation will be equal to ax plus bx squared. And then plus, and let's transform this one, that according with this will be equal to a prime x plus b prime x squared. Now we have an addition of two polynomials in the second vector space, right? I mean, an addition of polynomials of degree less or equal than 2. Let's add these polynomials. We have combined like terms here, this and this. This is going to be a plus a prime x plus, and this plus this will be b plus b prime x squared. So we can check that these things actually are exactly the same polynomial, so that means that property 1 is satisfied. For property 2, we need to take a polynomial and multiply by scalar. So we do k times a polynomial, like this, and we are checking if this is equal to this, which should be k out times the transform of just the polynomial. Well, as before, we do the left part, that is do first what is between parentheses. Let's leave the t out. The multiplication here is ka plus kbx. Now we apply t to this polynomial, which is apply this transformation, which says that is ka, which is the first term here, times x plus the second term, that is kb, times x squared. Okay, so this is then the transformation of the left part. And now we do the right part. So we need to do just this transformation here, so that will be k times, this transformation is just this, so that will be ax plus bx squared. Now we do distributive, just in the polynomials, and so this is kix plus kbx squared. And we check, and these are exactly the same. So that means that this transformation that we have here is really a linear transformation. We have here another example. In this case, the vector spaces are this one, which is the space of the matrix 2 by 2, and this is the space of the vectors in R3, the familiar vectors in R3. So this is a transformation that takes a matrix A, B, C, D and transforming the vector A plus B, C, D. So in this case, we can also try the properties in the same way. We have to check that when we do G, and so we take here an addition of two matrices, A, B, C, D plus A prime, B prime, C prime, D prime. And we want to know if this is the same that doing the transformation of just one matrix and then the transformation of the other, A prime, B prime, C prime, D prime, and then add them. So I leave to you then to do just as we did in the previous one. Do the addition of the matrices, then do the transformation. When you are done, do the transformation of these two, and when you are done, do the addition. If at the end, in both sides, you get the same thing, is that the first of the properties of linear transformations is satisfied. And then when you are done with that, you continue with the property 2 in the same way. You calculate k times a matrix first, do the transformation then. And then calculate just the transformation and then multiply by k. So if the two sides are the same, will mean that the property 2 is also satisfied. Okay, as before, we have the ideas of kernel and image, as we have it also for vector spaces in Rn. So the definition is going to be now that the kernel of a transformation is going to be the set of vectors in V such that they end up in the zero vector here. So if we have here the space V and we have here W and we have the transformation between them, so the kernel is going to be all the vectors here, and remember the vectors can be matrices, can be polynomials, can be anything in the vector space. So all the vectors here that end up in the zero vector here, the zero of the vector space W, this is going to be then the curl of the transformation. All the vectors that end up, that get transformed into the zero of the second space. And the image, in the same way, is going to be now in the other side, right? If we have the transformation here, so we transform all the vectors here, and they may end up all in something like this. So this part where they end up, this is the image of the transformation. So remember that it may be some vectors in W that they don't have any vector in V that get transformed in them. So the image is only the ones that do have a vector in V that they come from it. And now that we know what is a subspace, we can say also that both the kern and the image are subspaces. So are not just subsets of the domain and the codomain, but are also subspaces. So in that way, if, for instance, our first space is a space of dimension n, for instance, so we know that the kern is going to be some subspace of dimension less or equal than n. The extreme case will be when the kern is very, very small. I mean, when the only thing that transforms the zero W is actually the zero V. If that happens, so if the only thing that gets transformed, that gets mapped to zero, is just the zero, so then we're going to say that the map is injective. And if the image that can be very small or can be as big as the whole codomain, when that happens in that extreme, when it's equal to the whole codomain, we are going to say that the map is surjective, the transformation is surjective. We recall the names for the dimensions of this space. So now that we know that the kernel is actually a subspace, have a dimension, the dimension of the kernel is going to be called the nullity of the space, and the dimension of the image, I mean the subspace image, is going to be called rank of T. And you can verify the rank, this definition of rank coincides with the definition of rank that we have for matrices and for Rn, for the spaces of vectors Rn. Also, it's true the equality that relates these two numbers, that is very important equality, that says that the nullity plus the rank, the addition of these two dimensions, always adds the dimension of V. This equation is very important because the rank is a number that is very easy to calculate. So remember that the rank is calculated in different ways. I mean, one way that you saw calculated is just reducing the matrix and counting the number of pivots. So that is the rank of a matrix. Also, the rank can be calculated, the same number can be calculated as the dimension of the biggest determinant that is non-zero in the matrix. So in any of these two ways, so for instance, if you have a matrix like this, for instance, this matrix, you can check easily that the determinant is 0, so meaning that the rank is not going to be 3 here. But also, you can easily find a determinant like this that is non-zero, right? Because this minus this is minus 1, so this is not 0. So we found a determinant 2 by 2 that is non-zero, so we can say that the rank of this matrix is actually 2. So the rank of this matrix A is 2. So that's a quick way to calculate the rank. You can also do the reduction of the matrix, count the pivots, and you will get anyway that is 2. So considering that the rank is very easy to calculate, if we plug in the rank here, and we have the dimension of the space, so then we have a very quick way to calculate the dimension of the kernel. So since the dimension of the image is actually the rank, and we know that when the image is the whole W, so then it's surjective, so we can deduce right away that if the rank is the dimension of W, then the map is surjective. But then we can also deduce when it's injected, also depending on the rank, because we know that a transformation is injective if the kernel is 0. That means that the dimension of the kernel is 0. So if the dimension of the kernel is 0, we get that the rank is V. So in that way, we get a very quick characterization of injective and surjective by just looking at the rank. If the rank coincides with the dimension of the codomain, is surjective, and if it coincides with the dimension of the domain, is injective. And of course, if these are equal V and W, it may coincide with both, and then will be injective and surjective. And in those cases, you know that that is called a isomorphism. So we are going to say that a linear transformation is an isomorphism when it's injective and surjective. And in those cases, when there is an isomorphism between V and W, we are going to call these spaces isomorphic. And these are going to be very important spaces that are isomorphic. Isomorphic means that they have like the same form, so that essentially are the same. Let's say that is an idea of sameness, so that if the spaces are isomorphic in some way, let's say they are the same. And a very important theorem in linear algebra is this, which says, surprisingly, that all vector spaces of dimension n are actually isomorphic to Rn. In other words, there are not much variation of things in linear algebra. Essentially, everything is Rn. So we can consider polynomials, we can consider matrices, but this theorem says that even though we consider polynomials, they are going to have the same structure, the same form that Rn. So this isomorphism here is, let's call it In, an isomorphism from any space, any vector space of dimension n to Rn. This isomorphism is going to describe the same form, the same structure that the space of dimension n has, like Rn. For instance, let's consider the isomorphism like I3, a space of dimension 3. So what vector spaces of dimension 3 we know? Well, P2, for instance, right? So the polynomials of degree less or equal than 2, remember that is a space of dimension 3. Well, as such, should be isomorphic to R3. So what will be the actual isomorphism? What will be the bijection here between the polynomials and R3? Well, let's consider a polynomial of degree less or equal than 2, like a plus bx plus x squared. We can send it in what vector of R3? Well, the vector a, b, c. This is the isomorphism. By consider this translation, let's say that any polynomial will translate in this vector, so then we can consider that the space of the polynomials is actually the same, essentially, than the space of vectors of 3 coordinates. And we did it with the polynomials of degree less or equal than 2, but of course you can do it with any vector space of polynomials. And we can also think of other vector spaces we know. For instance, let's consider the matrices of 2 by 2. So this we know that is a space of dimension 4. So the isomorphism, let's call it I4, the isomorphism goes from the space of matrices 2 by 2 to R4, right? Because we are saying that is dimension 4. So what will be the isomorphism between them? Well, a matrix A, B, C, D, we can transform it in the vector A, B, C, D. So in that way, we can consider any matrix actually as a vector in Rn. We are going to say that this isomorphism from any vector space to Rn give us the coordinates of the vector. So we can say that if we have a vector here in certain base, this isomorphism give us the coordinates. This vector that is associated in Rn is going to be called the coordinates of the vector.